hello. Let's get into your first lesson of your last unit. This is wave properties. Okay. So first, what is a wave? A wave is any disturbance that transfers energy from place to place. Okay, so looking at this picture or this GIF, that person is pushing the slinky back and forth. So that push is creating energy, and that energy is moving from the top of the slinky all the way to the end of the slinky. Okay, so that's a wave. It's distributing energy from place to place. Then there are types of waves. There's a mechanical wave and an electromagnetic wave. A mechanical wave needs to move through matter, like solids, liquids, gas, just a medium, and cannot travel through a vacuum. A vacuum is an area with no matter. So an instance or an example of a vacuum is space. Space has no matter. An example of mechanical waves are ocean waves and sound waves. Then we have electromagnetic waves. The difference between a mechanical and electromagnetic is that an electromagnetic wave transfers energy without the use of matter. It does not need matter to create a wave. Okay, so it could travel through space. An example of those are X-rays, microwaves, and even visible light. Okay, because light from the sun has to come here through space, and it does not need matter to do that. Okay, so first let's talk about transverse waves. Transverse waves travel perpendicular to the direction of the source of motion. So for instance, this GIF right here, that person is going back and forth. It is moving in a direction that's perpendicular to the source of motion. So he's moving up and down. The wave is traveling left to right. Okay, so perpendicular. So he's going up and down. The wave is going left to right. Okay. So again, an example is moving a rope up and down. So I have a string right here, up and down. As I'm going up and down, the wave is moving across. And example of those, again, is moving a rope and waves actually coming from the television. So those waves are how we see pictures on the TV. And just something to note, electromagnetic waves are always transverse waves. They're never longitudinal. Okay, so here's some definitions that come with transverse waves. So a crest is the height of a wave. So the highest point of the transverse wave is a crest. And then the trough is the lowest point of a wave. Okay, so the tippy top is the crest, the bottom is the trough. Okay, so if we're thinking of a straight line, that would be the equilibrium. So anything above that line is its amplitude. That's how high the wave is. Okay, and then we measure the wavelength from crest to crest or trough to trough. Okay, so that's just the whole length of the wave is from crest to crest or trough to trough. Okay. Now let's talk about longitudinal waves. These are waves that travel in the same direction as the vibrations that are produced. Okay, so just the opposite of what a transverse wave, it's going the same way as the push. Okay, so if I'm pushing a slinky back and forth, or even like a one of those balloons that are stuck to the string, that's pushing the waves back and forth. Okay, so it's not going perpendicular, it's parallel to each other. The push is the same direction as the wave. Okay, in a transverse wave, that's the opposite. The push is opposite to the wave. Okay, so an example of these are sound. A sound is a transverse wave. A longitudinal wave. Stretching and pulling a slinky also shows the longitudinal wave as well. So that bottom picture right here. So here's the anatomy of a longitudinal wave. Okay, so this is the whole wave. There's two compressions. The compression is just the tightly packed particles, and then there's like the regular particles. The tightly packed particles to the next tightly packed particles is the wavelength. So from compression to compression, that's the wavelength. There's no crest, there's no troughs, there's just compressions. Okay. Next is surface waves. That's a mixture of both transverse, so the ones that are going opposite from each other, and longitudinal waves. Okay, so it's both at the same time. So we see the transverse wave pretty easily, right? But you could also see that the particles are coming together and then going back to normal. So they're compressing and retracting, okay? But they're also pushed away from the source of motion. Okay, so they're a mixture of both. An example for this is an ocean wave. Next, let's talk about wave properties. So a wave has a wavelength. They always have the length or the distance that a wave travels before it repeats itself. Okay, so for a longitudinal one, it again is measured from compression to compression. So from that one tightly packed part of the slinky to the next tightly packed part of the slinky is the wavelength. Okay, so from here to the red, that's one rate wavelength, and then from the red to the black is another wavelength. And then in a transverse wave, it's measured from crest to crest, from the highest points to the lowest points. So from here to here, that would be one wavelength, okay? Or you could say from trough to trough, right here from right here, that's one wavelength, okay? So again, a wavelength would look like that in a transverse model. So from the tippy top to the next tippy top, okay? And then this is showing a longitudinal wavelength. So the compression, the tightly packed coils to the next tightly packed coils. That's one wavelength, okay? And then every wave has a frequency. A frequency is just the number of times a wave repeats itself over a given time period. So if we count 1 second and a wave goes up and down, up and down, up and down multiple times, that will be 4. Okay, yeah. So if we look at this frequency is higher than the lower frequency because there's only 2 wavelengths here. Okay, so within this given time period of how long the GIF is. So if it goes from the tippy top to the next tippy top, all right, there's only 2 wavelengths. I'm sorry, there's only 1 real wavelength. And then this one right here has 2 waves, almost 3. Okay, so just the number of times a wave repeats itself. You don't need to calculate it for this unit. You just need to know that frequency is the number of times a wave repeats itself in a given time period. So it's also measured in the unit hertz. So hertz is just 1 wave per second. So instead of saying 1 wave per second, we just say hertz. Okay. Then there is a speed of a wavelength. That is a distance a wave travels in a certain amount of time. Okay, so how far it travels within a certain amount of time. Just some facts. Light travels 1,000,000 times faster than sound through air. Okay, that's because air travels faster in solids. Light travels faster in water than in glass. And sound travels 3 times faster in water than in air. Okay. So those are just some facts, but all you really need to know is that speed is a distance a wave travels in a certain amount of time. Okay. Then all waves have energy because they're transferring energy from place to place. So the wave energy is how to see what energy, how much energy it has. It's just a faster vibration. So the more vibration or the more frequencies, there's more energy. Okay. We could also calculate that by a larger amplitude. So if we remember what amplitude is, that's the amount, the highest point of a wavelength. So if there's more or a larger amplitude, there will be more frequency and more energy. Okay. Because if we see in this one with a lower amplitude, there's not as many wavelengths per time. That would mean there's a lower frequency than this one. That means there's a lower energy. Okay, so that is all for our first lesson. I hope you learned something new, and if you have any questions, message me, and I look forward to seeing you again soon.